All right, in the last part of our little video series on the Freescale line scan camera, I wanted to review the actual code that comes with the Freedom TFC board, the Google code. So we're going to look at the current revision of the Freedom TFC code line scan camera and show you how the code is implemented in C. So, and you can relate that back to the last video, and we talked about all the interrupt timing and whatnot. So, to use the camera, you don't necessarily need to know all the details here, but I want to show you how it works. That way, if you want to modify, because there's a couple little things that would be neat to modify on your own. So, the first thing I'm going to point you to is two different files. In the TFC library, there's this linescancamera.c, and then there is also tfc-adc.c. So here's how they're related. Linescancamera.c it doesn't have a ton of code in it. It just has some initialization of some of the peripherals and some of the I/O and working buffers, where TFC-ADC.C kind of has the meat of everything related to the analog digital converter. So what we're going to do is take a look at first linescancamera.c. So right off the bat, I meant, we're going to take a look at kind of like the working areas for the image data. So in this version of code, all the data recorded is 8-bit. Now, the Kinetis has a much higher resolution, but 8-bit's fine for this application. And if you want to convert this to use 12-bit or 16-bit, that'd be fine too. But kind of at the core of the routine is the working buffer. So there's two arrays, and these are dual two-dimensional arrays. One is for image 0 and image 1. This is for the two different cameras. So this would be for like camera 0 on the board. This would be for camera 1. Now, the next thing you notice, this is a 2D array. We have 128 pixels. And we have two sets of those 128 pixels. The reason is that we need kind of a foreground buffer and a background buffer to implement the ping pong. So while we might be reading out of one, we're writing to the other. That way, there's less chance of interference. Now, I'm going to have a variable that keeps track of what I'm calling the working buffer, meaning it's a number of 0 or 1 that points to where the ADC is dumping data to. And so if it's 0, then 1 is the index of the array that we want to be reading out of. Now, to make the scheme useful, I declare a handful of pointers, and they're just pointers to 8-bit data that kind of indicate to like a foreground loop what's going on. And so you don't actually directly are going to use the image 0 buffer. The driver is always going to point this pointer to the proper place to go. So you can use this pointer with some array notation for camera 0, and same with this one. The working buffer is used internally. You don't necessarily need to use that. So at the end of the day, line scan image 0 and line scan image 1 are what you want. And these could be an array of pointers. I just chose to keep them separate. It really doesn't matter. So this statically allocates the actual working area for the ping pong buffer for camera 0. This statically allocates the working area for camera 1. And we have some pointers pointing to the data. So the camera setup is done like so. Init TFC line scan camera, the first thing it does is sets up the I/O. So what I/O do you ask? Well, we need the clock signal and the SI signal. We need the A to D converter channels to be set to inputs. We need to set the pins as outputs. I kind of set the clock in SI to a a default value. And then I set up some of these pointers. So you notice the working buffer I set to 0, and each of the pointers for the working buffer pointers, I point to the address. I start at the 0 set, and I start at the beginning of that array. Likewise for line scan image 1 buffer, the same thing. Now the actual image data, I set it to the address of 1, because if the working buffer is at 0, the address is 1. And I just kind of directly coded it in right here. And we're going to see later it's all indexed with this line scan working buffer. Now, the other piece I have here is I have a function called set exposure time. This sets the integration time, and it's to first order fairly accurate. I just set up the PIT, the programmable interval timer, to interrupt at like a certain rate in microseconds. Now I'm going to come over to, in TFC, we're going to see how this is initialized. So I initialize the ADCs, then I call this initialize line scan camera data. So let's take a look at init ADCs. Now this file has a lot of functions. There's a driver from the Kinetis sample code that I kind of used. And I have this init ADC 0 function. Just for now, let's just you can read through it. It's from their sample code. It just sets up the converters for 8-bit mode. And there's quite a bit there, and you can kind of take a look at that. But what I want to look at is the actual higher level function, the init ADC. So the first thing we do is set up ADC channel 0. The next thing I want to tell you is that to handle all of that behavior in the interrupt routine, there's a state machine. And the state machine just uses an 8-bit number to maintain state. And you notice the first thing I do is set up to the init state. The next thing I do is enable the programmable interval timer, and then I set the exposure time. The next thing I do is I enable the PIT 0 and its interrupt. I enable the clock here, but this is where it's actually enabled. Enable the PIT here, and then I turn on the interrupts for the PIT and the ADC. So at this point, the programmable interval timer, will fire, at whatever this default exposure time is. So I think I set it here. This is 5,000 or 50,000 microseconds, which is 50 milliseconds. That's actually kind of slow. It could be faster, but that's just for an example. So once this is set up, our A to D converter is ready to convert, and the PIT is going to start generating interrupts. So we're going to start in at kind of the beginning, like in that state diagram, I showed you earlier, the graphical. So here's the PIT IRQ handler. So whenever we get the IRQ, the first thing we want to do is bring SI high. That kind of flags the camera to start. But remember, before we do any camera data, we capture the potentiometers and the in the battery channels. So what I do is I tell my state variable that I'm in the mode where I'm capturing pot 0. And what I do is I set up the multiplexer and the status and control register to go to pot 0. And if you read through the data sheet on the analog digital converter, as soon as you write to this registry, select the channel, and in this case I told it I want interrupts enabled, it'll just start. That's its kind of start conversion. And that's the way I've set up in the init routines, is that it's a software start anytime you write to that register. All right, next is everything else from this point. I say that we've primed the pump. Everything's going to start flowing here. So once we start the first conversion, every time we're done, we're going to jump to this ADC IRQ handler. So the first thing you're going to notice is that I do a switch. I look at the current ADC state, then decide what to do. So after the PIT interrupt goes active, I set the state to capture pot 0. So I know the reason I have the state variables, I kind of know what to do with the data when I get it. So it's just a way of keeping track where I am. So here, the first event is I capture pot 0. Well, I have an array I'm storing the value to hold it for if someone needs it later. Then the next thing I do is I set up a conversion for pot 1. Then as soon as I do this, I also set my state variable, say, hey, that's where I'm at. Then I leave the interrupt. The interrupt has nothing else. It's all it is this switch statement. So if I go down here, when I get past all the cases, it just leaves. So it'll go back, the program will go back to doing whatever it was doing before. Then eventually we're going to get here where we're capturing pot 1. Same thing, I'm going to dump the result in temporary placeholder. Then what I'm going to do is I am going to start conversion on the bat sense channel, all right, and then set my state appropriately. When that conversion is done, we're going to jump back to this interrupt, but it'll be in this case. I store the value, in a temporary placeholder. And then notice what I do here. I assert high, clock high, then low, according to my drawing. And then what I do is I get ready to set up for reading the camera. And I have two other variables, current line scan pixel and current line scan channel. That's going to keep track of which pixel I'm currently recording. So I'm going to set it for line scan channel 0. And when I jump, the next time I get an interrupt, I will be in this state here. And all I do is I say, is my current pixel less than 128? If so, I look at the channel I'm on. If I'm 0, that means I dump the result from 0 in the working buffer for channel 0, and then I start the conversion for channel 1. And then what's going to happen is after I am done with channel 1, that means I'm in this else clause here, I'm going to increment my current scan pixel and then toggle the clock. All right? Then this is just going to keep this, as long as current line scan pixel is less than 128, every time I interrupt, I'm going to come back here. Because I'm incrementing here, I acquire 128 samples, I come to this else clause. The last thing I do is toggle the clock once more, because the data sheet says you have to. And I reset the state to this init state. And lastly, I swap the buffer. Now, looks like there's a lot here, but it's pretty simple. All I do is I look at what's my current working buffer, my current index. If it's 0, I make it 1. And then I just flop these pointers around. All right? So you notice here, image 0 working buffer actually goes to the 1 index instead of 0. Same with the other channel. The image, the actual data we're going to read, goes to the other side of the buffer. Like I said, if we're in this else clause, that means our working buffer was equal to 1, and we just flop the pointers the other way. So the last thing I do then is I set a flag saying that the line scan image is ready. So you can look at that in a foreground loop to say, hey, you have a new a buffer to read from, and you just always use this pointer here to grab the data and do what you want. And that's it. That's the whole program. It's kind of cool how it's all an interrupt. It'll take a little bit to wrap your head around, but study that timing diagram once again and listen to this video and read through the code. I feel this is a really good example of an interrupt-driven code because it uses 2 interrupts and kind of makes good use of the peripherals. Now, the only other thing I could possibly want to add to this is add a third interrupt where I'd want to use direct memory access, where when I'm all done, I might copy, one of the buffers into a third buffer, make a triple buffered to be really, really safe. Now, let me show you real quick. We're going to show this in another video how this works again. So in my main loop in main.c, and I'll go right to where it's at, here's how you can use the API. I have a main loop here that goes through these different cases this over and over and over again. And I just say, and my grade is a ticker, I wait every 100 milliseconds, and I say also, is there data ready? And if so, I reset this flag to say, okay, so next time I come around, I know that I've already read this buffer. And without looking at the details here, you can directly use that pointer and just index it, like you would an array to grab the 128 samples. In this case, I'm printfing to a terminal. I'm going to explain this terminal printf, in a different video, but that's how you use it. You literally just use this pointer as an array. The only thing you want to do is you want to key off this variable right here. And generally, whatever you do with this working buffer, you want to do quickly, because there is a possibility that you'll have a buffer switch in the background. So you almost immediately want to copy data out of that. You only want to use it for a temporary buffer. You don't want to sit there for a long time, or else you'll be switched over or to the other buffer, and that could be bad. So, all right, so that was a quick introduction of where to look to see how the driver code works. Like I said, I think it's a really good example of a hardcore, embedded systems driver. So I hope you enjoyed this little series and you learned something.